Alright guys, here is a video for the Chapter 10 review, and I'm sorry if it's fast, I just kind of want to get it done with. So, feel free to pause it at any time and slow it down. So question 1, we're given a series, and we're going to find the radius and the interval convergence for the first part. So first thing I'm noting is that it's a geometric series, and it's a power series as well. And a power series will converge if a power series will, a geometric series will converge if the common ratio is less than 1. So since the ratio is equal to x minus 6 over 7, well then this will converge, so x minus 6 over 7, the absolute value of it, will converge when it's less than 1. Or if you multiply both sides by 7, you get the absolute value of x minus 6 is going to be less than 7. And now that I have x with no constant minus or adding another constant, and this over here is the radius. So the radius of the the radius of convergence is going to be 7. And the interval, well, if I do x minus 6 and I split up the absolute value to be between negative 7 and 7, and then I add 6 to both sides, I get x is going to be less than 13, but greater than negative 1. So here's the interval, and there is the radius for the geometric series. Next part is to find the function of x, which represents the values of x for which the series converges to. In English, that just means what is the function that represents the series that's going on up here. And if you remember, the sum of a geometric series is the first term divided by 1 minus r. In this case, the sum is actually a function. So f of x, that's why it's a power series, so f of x will be equal to the first term. Well, the first term, so if I plug in 0, anything to the 0 power is 1, so the first term is going to be 1, and then 1 minus r, and r is up here, so x minus 6 divided by 7. And I'm just going to tidy things up here, get a common denominator, so this would be 7 over 7, so 7 minus 6 minus x plus 6, so this will be equal to 1 over 7 minus x plus 6 divided by 7, which is equal to 1 over 13 minus x over 7, which is equal to 7 over 13 minus x. And this is my function right there. And also, this is the function that it converges to, but only upon the interval of negative 1 to 13. Alright, so this is, if I want to do so, that's alright, so this is equal to this series up here, infinite series. Okay, for 3, find the power series for d dx of f of x, show the derivative as well. So what we've just concluded from over here is that 7 over 13 minus x, which is our function, is equivalent to the infinite series starting at n equals 0 of x minus 6 over 7 raised to the n. And just for the sake of illustration, not that you have to show this, but this is equal to 1 plus x minus 6 over 7 plus x minus 6 over 7 squared, all the way to you get to x minus 6 over 7 to the nth, and then n plus 1, and so on and so forth. So not that you have to show this, it's just it helps me to visualize what's going to happen for these next two steps. And so find the power series for the derivative of f of x. So first of all, let's find what the derivative of f of x is. So the derivative of this function right here. So you have 7 and then 13 minus x to the negative 1. So I'm going to have to drop this. So it's going to be negative 7. And then this is going to be 13 minus x to the negative 2 multiplied by the derivative of the inside, which is negative 1. So in short, we're going to have 7 over 13 minus x squared. So this is our function, and I'm just going to delete this so I have more room to work with. So here's the derivative of our function, but what is the power series? So that means to find the power series for this function. So the power series will be derived from this one right here. So we'll use the derivative of each of these terms. Well, the derivative of 1 is going to be 0. So we don't need that. The derivative of this term is going to be the coefficient of x, which is 1 over 7. Okay, the derivative of this term, I would have to drop the 2, decrease this by 1, so it's going to be 2 times by x minus 6 over 7 to the first power, multiplied by the derivative of the inside, which is 1/7. And then I'd keep doing that until the nth term. And so the nth term, I would drop the n, decrease this by 1, so n minus 1, multiply by 1 over 7. So my power series, I'm going to hold off on this part until after this next part. So the power series is just the actual written notation is just the series of your nth term. So I know what's happening, I've observed the pattern, but the nth term is what I'm going to show for my series. So I'm going to drop the n, so there's going to be an n, and then I'm going to have x minus 6 over 7, and then this is going to be to the n minus 1 because I have to decrease this, and then I'm going to have to multiply by the derivative of the inside. The derivative of the inside is 1/7, so I'll just multiply that on the outside here, so 1/7. Okay, and so now the first term of this series should be equal to 1 over 7 because that's the derivative of that term right here. So in that case, I want n to be equal to 1 here, because if n is equal to 1, then that's going to be 1 over 7, and if this is 1, that's 1 minus 1, so everything's going to be to the 0 power, so I'll be left with 1/7. So there's that right there. So now you no, I think that's actually pretty good. So didn't really need a whole lot of space there. Maybe because I wrote it up here, but in any case, I'll actually probably just take this down with me for the next part right here. Okay, so as for this part, we're going to do the same thing, but we're going to find the integral, or the antiderivative for this. So find the power series for the integral from a to x of this function right here. And so show the antiderivative, and then we're going to show the series to represent it. So the derivative of this would be 7, and then natural log of 13 minus x. Let me hold up for just a second. I'm going to use more appropriate notation. So we're going to do the integral from a to x, because I want to explain this a to x. So a is the center of your approximation. If you don't know the center of your approximation, look to your power series. This is the center of your approximation where it shows x minus 6. Positive 6 is the center of your approximation. So this should be from 6 to x. And since I'm using the upper bound as x, I'm going to use the variable t as a dummy variable, which will be replaced with x. Okay, so there is my setup for my integral slash antiderivative. Now we'll do the integral. So that's going to be 7 times by the natural log of 13 minus t. And then I have to divide by the chain rule. I would have to divide by the derivative of the inside, so that would be -1. So that's going to be -7 right there. And then, of course, from 6 to x. And so with that being said, let's evaluate our bounds. So I'm going to plug in my x. So I'm going to get -7 natural log of 13 minus x, and then plus, because I have to subtract the lower bound, and my lower bound's already negative, so 7 natural log of 13 minus 6, which is going to be 7. Okay, so I've found the function. Now I need to find its power series representation. So I'm going to do the same thing. I'm going to, just for sake, I'm going to do the integral from 6 to x dt, and let's just imagine these are all t's right here. So Now, when I anti-differentiate this, I'm going to get t right here, since I'm integrating with respect to t, so I'll get, this is just for illustration really, I'll have t and then plus, well, for this part right here, I have to increase the power, so this is going to be t minus 6 divided by 7. I'm going to have to increase the power, so it's going to be 1 plus 1. I'm also going to have to divide by 1 plus 1, and I'm going to have to divide by the derivative of the inside because of the chain rule. So dividing by 1/7, so that's just going to put 7 in the denominator here, just like that. Okay, I think I did that. Divide by 1/7. No. Dividing by 1/7 is going to put that in the numerator. Yeah, because keep, change, flip. Okay, sounds good. That's a very ugly way to write it, but I'll clean it up in the next step. So then we'll do plus, okay, and then we'll continue the pattern eventually until the nth term. And so for my series, I'm going to have my series, and what's I'm going to write in my nth term because that's what I need to do. So the series should just be represented with the nth term. So again, the nth term, this has to be added. You have to add 1 to that when you take an antiderivative. Let me give me a little bit more space here. So this is going to be 1 second. So taking the nth term, this is going to be t minus 6, and then divided by 7. That's not going to change. This is going to be n plus 1. So this is how I'm going to, I know I have to multiply by 7 because we have to divide by the derivative of the inside, and then I'm going to divide by n plus 1. Okay, so this was that part right there, 1 plus 1, the next one would be 2 plus 1, this would be 2 plus 1, so on and so forth, and then we're always multiplying by 7, so that looks pretty good to me. That would be our nth term, and of course this would be from 6 to x. Now we'd plug in our x, so we'd plug in our x here, we'd plug in our x here, now, and for every term, and then when I plug in my 6, note that it will all go away. So this would go away, this will go away. The only term that it's not going to go away for is this one right here, but you don't have to worry about that because, well, I talked about it at the very beginning whenever I first introduced this, but so the first term, it's going to go away because if I were to, I'll show you in the next step, maybe if I have time. So in any case, this is going to be from n equals 0, this is going to be 7 to the n plus 1, t minus 6 over 7 to the n plus 1. So this is my power series representation. You could have also chosen to written it, some people, depending on how you actually found it, it could also be written as 7 over n plus 1, and then t minus 6 to the n plus 1 over 7 to the n plus 1. So pretty much I'm dividing the n plus 1 to both, or I'm putting it to both the numerator and the denominator. And here it would simplify to just be 7 to the n in the denominator. So the series n equals 0, you would have t minus 6 to the n plus 1 all over 7 to the n times by n plus 1. So these are some different ways that some might have done it depending on how you simplified this part right here. Okay, now as for the last part I was talking about with the terms, so if I were to write out the terms here, I would get, so plug in 0, I would get 7, and then I would have t minus 6 over 7, just like that. Now this right here, if I were to simplify this, I would get t minus 6 as my first term. Okay, now the thing is, up here, my first term was t, not minus 6. So where is this minus 6 in my power series? Where is that along here? So it's all the way in the last part right here. So yes, I'm going to plug in x, and then that's going to turn everything to x, which is where this is. So if I plug in x here, I get the x here, or t or whatever. But if once I plug in my lower bound, remember that I'm going to subtract this right here. So that's where this other this other 6 is going to end up. So whenever I plug this into my lower bound, I'm going to subtract it. And so all the way after all these many terms, when I plug in my lower bound, I'm going to get dot 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 minus 6. And so that's where it's hiding in this part right here. So that's why it's t minus 6 as my first one. Okay, but in any case, all I'm pretty much saying is that you don't have to worry about plugging in this lower bound. It's all taken care of, is what I'm saying. Okay, so with that being said, I think that wraps up this problem right here. We have the antiderivative of the function and the power series that represents it. Okay, onto this next part right here. Taylor, just one other note, that just as for the function was over -1 to 13, that was the interval. That is also applies to the derivative and the antiderivative. So these are equivalent, but only over this interval. Okay, and then let's go into this next one. So find the third order Taylor polynomial that represents the function. So for a Taylor polynomial, note that each term can be found. So first you need to find the coefficient of each term. That would be helpful. So the coefficient of each term in the polynomial is the nth derivative at the center. I guess we'll call it A. Some people call it C. Some people call it A. Divided by n factorial, and then x minus A, the center, to the nth power. So this is a Taylor polynomial. I guess this is a Taylor polynomial right here. We'll say, yeah, n equals 0. So this is a Taylor polynomial. This is the coefficient, and then this is the variable part. So what I want, since I'm building a third order Taylor polynomial, I'm going to go to the third degree or third derivative. So first of all, I'm going to want the 0th derivative at the center, so f of 5, which would be e to the 20. Now I want the first derivative of x, I want the second derivative of x, and I want the third derivative of x. So first derivative is going to be equal to 4e to the 4x, and the second derivative is going to be equal to 16e to the 4x, and the next one's going to be equal to 64e to the 4x. Okay, so this is how I write out my Taylor polynomials, so if it doesn't work for you, that you can do your way. Okay, so but now I need to know the first derivative at 5, the second derivative at 5, and so on and so forth. So the coefficient, let me give me a little bit more space. So the first coefficient, well, the first coefficient's here, but I guess the next term coefficient is going to be the first derivative at 5, and so that's going to be equal to 4 e to the 4x, but I'm also going to divide by 1 factorial. So this is divided by 0 factorial, this is divided by 1 factorial, which won't affect it for either of those. For the next one, so the second derivative at 5 is going to be 16 e to the 4x, and divided by 2 factorial, which is just 2, and then the third derivative at 5, which would be 64. Wait, what the heck am I doing? 1 second. This should be 20 right here. I need to actually plug in my value. Sorry. 20, 20, and then this is e to the 20 divided by 3 factorial, which is going to be equal to 6. So in any case, p sub 3 of x, I now have the components. I have my first term. My first term right here is going to be e to the 20, and then we're going to have plus 16 e to the 20 divided by 2, and then I need to make sure I include x minus 5 as well. The next term is going to have that should be 4 right there. Sorry, I'm obviously trying to get this done way too fast for my own good. 4e to the 20 x to the 5th. Next term is going to be 16e to the 20 divided by 2 factorial, and then x minus 5 squared, and then the last term is going to be plus 64 e to the 20 divided by 6, and then x minus 5 to the third. So there are my terms. If you want to simplify these coefficients, more power to you. I think I'm just going to keep powering through. Okay, so for this next part, find the Taylor series, not the Taylor polynomial. So the Taylor series, I'm going to wait off until I know what I want to start this with. But my nth term, what would my nth term be described as? My nth term, well, I notice that I always have an e to the 20. So there's always going to be that. So it's going to it's going to have to include that. Also, each term is 4, so this would be 4 to the 0, this is 4 to the first, this is 4 squared, this is 4 cubed. So every term has 4. That's because when we take the derivative of this, we keep multiplying by a 4. So I have to include 4 to the nth power, and then e to the 20, that's going to be my coefficient divided by n factorial. So there's my coefficient, and then I'll have x minus 5 raised to the nth power, and so that means I want n equal to 0, because that's going to be 1, that's going to be 1, that's going to be 1, leaving me, yeah, so n equals 0. So here is my series. So again, the coefficient, this is my coefficient. The first nth derivative at a divided by n factorial. The nth derivative at a is how we got this part right here. And yeah, so there's our Taylor series. Okay, 1 second. Okay. Find the first 4 non-zero terms of the Maclaurin expansion of the given function. Okay, so sorry, let me collect my thoughts. Find the first 4. Okay, so first 4 non-zero terms of the Maclaurin expansion of the given function. So here is e to the x, and here's its Maclaurin expansion, but it's only giving me 3 terms, so it's not too bad. This is the third term is just going to be x to the third over 3 factorial. The nth term is going to be x to the n over n factorial. Okay, so let's go ahead and find what the Maclaurin the series would be for this one right here. So first I'm going to take this right here, e to the x squared. So if I want to know what e to the x squared is, then I'm going to use this expansion right here and just substitute x squared in for these terms. So e to the x squared is going to be 1. It's going to be equal to 1 plus e to the x, sorry, nope, it's not. It's going to be x squared plus x squared squared, which is going to be to the 4th divided by 2, and then plus x squared to the 3rd, that's going to be x to the 6th over 6, right? So, okay, or 3 factorial, right? And then that would go to the nth term, which would be x to the squared to the n, which would be x to the 2n and n factorial. And then if I want to multiply by x, okay, so multiply by x, so x times by e to the x squared, you have to multiply each term by x, so it's going to be x plus x to the 3rd plus x to the 5th divided by 2 plus x to the 7th divided by 6 or 3 factorial, plus now the next part is the general term. So give the general term for the nth term. So I'll just write it down here. So the general term, that would be x to, so you'd have x times by x to the 2n divided by n factorial, which would be x to the 2n plus 1, since you can add the exponents, and then n factorial. So that would be the nth term right there. Yep. Of the series above. Okay. Yeah, that's all I need for the nth term. Alright, so approximate the value of the given function by using 3 terms of the appropriate Maclaurin series. Okay, so we're approximating this. So using 3 terms, and we're given 3 terms. Okay, so one thing is I need to know what x is. So 1 plus x in this case has to be equal to what's inside, so 1.125. And if I subtract 1 from each side, I get x is equal to 0.125. Okay, and so this is where I'm going to approximate it. So this will approximately be 0.125 plus 0.125 squared divided by 2 plus 0.125 cubed divided by 3. So you could punch that into a calculator and use a store function. So I'll do 0.125 store as x. Okay, and then let's go ahead and punch this in. So I'm going to have x, and then minus, I'm going to have x squared, and I'm going to divide that by 2, right? Yeah, divide by 2. And then we're going to have plus, and then we'll have x raised to the third, and we're going to divide that by 3. And there we go. So that right there is our approximation. So this will be equal to about, our approximation is 0.117839. Now if you want to check your work, let's actually plug in the natural log of 1.125. It's a pretty good approximation. Okay, what is the error bound of your estimation according to the alternating series error bound? So you can note that this is an alternating series with positive, negative, and the next term would be negative. So the alternating series error bound. So this says that the error has to be less than or just less than. Has to be, it might be equal to, I can't remember. Has to be less than for sure the absolute value of the nth n plus 1 term, nth plus 1 term. Now the nth plus 1 term in this case would be negative x to the 4th divided by 4. Okay, so this would be equal to, since I'm using absolute value, don't need the negative, 0.125 to the 4th divided by 4. And if you punch that into a calculator, so we'll have x raised to the 4th divided by 4. And that's what we get, 6.1034 times 10 to the negative 5. So 6.104 times 10 to the negative 5. This is the most the error could be. So pretty good approximation. If that's the highest the error could be. You can also kind of check and see how good this matched up with the previous problems right here. So this was our approximation, and if we subtract away this right here, you can see that we are underneath that, or we are well within our bound. Okay. Alright, now the Lagrange error formula, which I know everyone's just completely confused about. So yeah, I'm probably going to do these next two, and then I'll do a video for a different video to cover the rest of that. Just because I gotta go do something. Okay, so suppose you use p sub 2 is equal to this right here. Now, yeah. P sub 2, yeah. I assume they're saying p sub 2 because it's the first two non-zero terms of this. Now, if you're familiar with the Maclaurin series table, which I hope you have some familiarity to it, you should know that sine of x, this is what sine of x is equal to. So we're given the sine of x Maclaurin series right here, which is helpful if you ever need it later. But in any case, that's sine of x, so we're centered at 0. And we want to give an error bound. Now, there's the Taylor theorem, just to remind people, which is where the Lagrange error bound is derived from. It's derived from Taylor's theorem. theorem, which is based off of Taylor series. Now remember, we had our definition of a Taylor series right here. This is the nth term. This was the nth term of the Taylor series. Now Taylor's theorem said this though. He said that the error of a Taylor series is equal to, he could actually find the actual value of the error, equal to, it's equal to, now if I rearrange this just a little bit to the notation that we use, it was equal to the nth plus 1 term. So everything happening at the nth plus 1 term. So n plus 1, and then the derivative at n plus 1. So n plus 1. But this was happening not at the center, but at some value z, where z was between the center and the approximation. So we'll just say center approximation. Now this at any moment, this could be switched depending on if you're approximating to the left or to the right of the center, but anyway, z is between these two values right here. So this was Taylor's theorem. He said that you could find the error by using the nth plus 1 term of the Taylor series, but your derivative happens, so this part right here happens at a value of z, not at the center. And he says that if you use that, you can find your exact error. But we don't know how to find that value in between our center and approximation, so that's where Lagrange error formula comes in hand. So he said that the error has to be less than the absolute value. Oh, we'll talk about that in a second. It has to be less than x minus a to the n plus 1 over n plus 1 factorial. That should be factorial. And then times by the absolute value of the maximum of the nth plus 1 derivative at z. And this value of z, again, is between here, but we're going to use the center or the approximation in order to maximize this. So in this case right here, this will be equal to, since we're centered at 0, and we have the third term, the next non-zero term is going to be x to the 5th and 5 factorial. So x to the 5th over 5 factorial, and we're going to use the maximum of the 5th derivative at z. Okay, so we can already start plugging in some stuff here. So we know that we're approximating at 0.25, that's the x value, to the 5th divided by 5 factorial. Now we need the 5th derivative of sine of x, because that's what we're using, that's what the function is right here. So 5th derivative of sine, if you do that 5 times, is going to be cosine. So this is going to be cosine of z. And z is going to be greater than 0, because that's the center, and then it's going to be less than 0.25. Okay, now one of these two values is going to maximize this. And so in this case right here, 0 would maximize cosine. So this is going to be equal to 1. And leaving us with just this right here as our error. So our error has to be less than, and if you put that into a calculator, so 0.25 to the 5th divided by 5 factorial, you get a very, very small number. I think it's like, let's punch it in. So we got 0.25, we have to raise that to the 5th. And then we have to divide that by 5 factorials. 5 times 4. I know there's a factorial button. I'm just too lazy to go to it. 5 times 4 times 3 times 2. Oh, I messed up. Hold on. So 0.25 raised to the 5th. Right, and then we're going to divide that by 5 times by 4 times by 3 times by 2. There we go. So we get 8.138. Yeah, I thought it started with an 8. 0.38 times by 10 to the negative 6. That's the most the error can be. Alright, let's try it one more time. In this exercise, though, it's not going to be centered at 0. So suppose we're using this polynomial right here to approximate here. Now this right here. Now notice that the function is centered at 2. So this is as if we're using e to the x minus 2, not e to the x. Okay. And so in this case, we x would be equal to 2.5 in order for this to be the same. Okay, so again, we're just going to use the formula. So the error has to be less than x minus 2 to the n plus, in this case, we'll just use 4 because that's the next non-zero term, divided by 4 factorial, since 2, 3 factorial, 4 factorial, yep. Okay, and then we're going to have the multiplied by the maximum value of the fourth derivative at z. Now the fourth derivative, so our function is e to the x minus 2, and the derivative 4 times over is still going to be e to the x minus 2. Okay, so then we have, we're going to plug in our value, so 2.5 for x, so we have 2.5 minus 2 to the fourth divided by 4 factorial times by the absolute value of e to the z minus 2. And then now z in this case is going to be so it's going to be 2 and 2.5. So this is our center, this is our approximation at 2.5, and which one would give this one a larger value? Definitely 2.5. So this is going to be equal to that's going to be 0.5 raised to the fourth divided by 4 factorial, and then e raised to the 0.5. So if we plug that into a calculator, so we have 0.5 raised to the fourth. Okay, and then we have to divide by 4 factorials, 4 times by 3 times by 2. Okay, we got that, and then we have to multiply by e raised to the 0.5, and we get 0.00429 as the maximum error, 0.00429. Okay, so that is Lagrange error formula. I need to go do something, so I'll be back and I'll post another video that will finish up on these examples.